All right, ladies and gentlemen, at this point in our study of the unit circle, you should be fairly comfortable filling in all of the items you see on this picture. You should have degrees, radians, and cosine and sine at all points along the unit circle. You might not be great at it at this point, but you should be pretty familiar with it. And based on knowing these points, you should be able to also find the tangent, secant, cosecant, and cotangent of all of these places. So what we're going to do today is inverse trig functions. Basically, we're going to do the process backwards. Instead of me saying to you, what is the tangent of 135 degrees? In which case you go over to the second quadrant, you figure out what the sine and cosine are, and you divide them, or you use other patterns to remember what the tangent is. I'm going to ask you this question. Friend of mine, tell me what angle or what arc in radians has a tangent value of -1. I'm going to reverse the process. Okay? Inverses, plus and minus, are inverses. They do the opposite. Log and e, or log and exponentiation, those are inverses. Square root and square. This is just another set of inverses, doing the process backwards to add to your skills. All right. If I want to ask you what angle has a sine of 1/2, I can write that in a couple of ways. Arc sine is short for, tell me the arc whose sine is 1/2. I could also write that as sine inverse, sine with a little -1 sign. Both of these things basically mean the same thing. I want to start with this. Sine inverse of 1/2 does not equal cosecant of 1/2. Very, very common mistake, all right, because you know that inverse, x to the -1, equals 1 over x. But that's just because the inverse of multiplying is dividing, all right? So when you multiply backwards, you divide, basically. So that is why, because that -1 you've been taught means move it to the bottom, the common misconception is, well, I must be able to move sine to the bottom, which is 1 over sine is cosecant. This is not the case. Sine inverse means do the sine process backwards. You tell me the angle whose sine is equal to 1/2. Okay, so arc sine, sine inverse mean the same thing. So how do you know if they want radians or if they want degrees? Well, our old school 1970s book does it this way. Inverse circular they want you to tell them the radian measure. Okay, so if I say, give me the arc whose sine, or give me the inverse sine of 1/2, and in the instructions it says these are circular inverse trig functions, then I'm asking you for pi over 6. If it's called a trigonometric inverse trig, inverse trig, short for trigonometric, I should write it, that's asking for degrees. Now, not every time, I'm not sure that all new textbooks use that terminology. Some way it will tell you. It might give you a domain where your answers need to be, and in that case it will either be in degrees or in radians. Something about the question will give you a clue. Do they want the degrees or do they want the radians? Besides that, arc sine and sine inverse both mean the same thing. All right, now, here's the thing. Every one of these questions, technically, I don't know about everyone, but most of them have infinitely many possible answers, okay? What you learned when you were learning about the unit circle is we don't just want to know 0 to 360. All right, we have done things like, how about, I don't know, 450 degrees. 450 degrees is 360 plus 90 more. All right, another way to say it is 30 degrees has a sine of 1/2. Well, so does 150 degrees, or 5 pi over 6. Well, so does 390 degrees. I'm back here again. And so does, let's see, 360 and 150 would be for 510 degrees. So if I say, what's the sine of 510? 1/2. What's the sine of 30? 1/2. What's the sine of negative 330? 1/2. There are infinitely many degrees / radians that have sine equal to 1/2. So if I say to you, tell me the angle whose sine is 1/2, there are infinitely many possible answers. So here's how we deal with that. The function version can only have one. We can talk more about the details of that, but the function version of this question it's just asking you for one value. You know how functions, there can only be one y for every possible x, passes the vertical line test. Again, our old 1970s book will capitalize either the A in arc or the S in sine inverse if they want just one value. Or they'll just be a domain given. So they'll say arc sine of 1/2 between negative 90 and positive 90 degrees. We'll talk about that in just a second. So again, some way or another, and we'll see in different worksheets or different textbooks that we use, it will give you a different way to know. Am I asking you for just one, or do I want all of them? This is the function version of these inverse functions. We'll talk about the graphs of them and how this connects, but for now, just the basics. Capital letter, give me the one value. Lowercase, I want all of them. All right, infinitely many. You need to represent all infinity possible answers. So before we get to infinity possible answers, if I want just one value, which one do I want? So make sure you get this little chart written down. If it is an arc sine, or an arc tangent, or an arc cosecant, I want the answer that lives between negative 90 and positive 90. That's for arc sine, should do capital because that's the one they're asking us for just one. Arc tangent, arc cosecant. And those are kind of the sine-based trig functions because it's sine over cosine, and it's 1 over sine. Kind of the cosine brothers of those. If I ask you, are going to be up here between 0 and 180 degrees. All right, this would be arc cosine, arc cotangent, and arc secant. So let's talk about why that's the case. If I say to you, what is the arc sine of 1/2, which I've been using as my example, why does it make sense to use quadrants 1 and 4 for my possible answers? Well, arc sine of 1/2 happens twice in our first time around the circle. Over here at 30 degrees and over here at 150 degrees. If I use the top like I would if this were arc cosine, I haven't eliminated my two answers. I could still give either one. And the goal of this function version is to narrow it down to just one answer. So if I restrict myself to over here, then the 30 degrees is the only one that could be my possible answer. All right, so I don't want to allow two possibilities. So therefore, arc sine of 1/2 is 30 degrees. It's the one value in the first and fourth quadrants over here that has a sine or a height of 1/2. All right, these two angles have the same sine because they have the same height. Now, that's how you decide which one of the infinitely many to do. So how are we going to deal with it if we're trying to represent all infinity of them? All right, obviously we don't want to write out infinitely many different answers. So let's talk about this. Arc sine of 1/2, or sine inverse 1/2. How can we represent all possible of the infinitely many angles that have a sine of 1/2? All right, so we talked about the fact that 30 and 150 are the ones that we need. Now, how do we represent all of those? Well, 30 is a possibility. All right, that's one of the infinitely many that I want to add. That's right here. Now, 30 plus a full rotation around the circle, that gets me back to 30. All right, and that is how many degrees? That would be 390, true? 360 plus 30 more. And then if I go 360 more and go 360 more, that's an infinitely long string, 360, 360, 360. If I subtracted 360 and instead I went negative 330, which is really just subtracting 360 from my original 30, I get that again. So this goes both ways. This is a never-ending string, all 360 away from each other. Now, the 150 starts another string like that one. 150 plus another time around the circle, which would be, I believe, 510. The negative version of 150, this one right here, would be negative 180 plus 30 more, which would be negative 210. And they go on and on forever. Now, I want to represent those in a nice, neat expression, all right? So here's how that goes. Arc sine of 1/2 is 30 degrees plus 360 degrees times n. And it's understood, you don't have to write this every time, where n is any integer. Okay, so if n is 0, I get to 30. If n is 1, I get to 390. If n is negative 1, I get the negative 330. If n is 2, I get the next one. If n is 3, it goes on and on forever. So that's all infinitely many possibilities. But there's also the ones based on the 150, so I'm going to do the same thing. Always add plus 360n to this type. Okay? So this is an expression for all of the infinitely many values of lowercase arc sine 1/2. Those are all angles who have sines of 1/2. Now, to get an example that's not in degrees, let's do a circular arctangent of, let's say, square root of 3. Now, arcsine and cosine, because sine and cosine are the ones that we naturally deal with, arcsine and arccosine are a little bit easier. Arctan, arccosecant, those type are going to take a little bit more thought. But what I will realize with a little bit of thought and reasoning and maybe some multiplying of fractions, dividing of fractions, tangent is positive square root of 3 up here at 60 degrees. And straight across from that at, how many is that? That would be 240. 60 and 180 makes 240. Okay, so again, you know the unit circle at this point, so you can convince yourself that the tan of 60 is square root of 3, the tan of 240 is square root of 3. Now, for tangent, it's going to work slightly differently. These, the fact that they are right across from each other, if I can get one of them, if I can get the 60, then I can just add 180, add 180, add 180, add 180. So that cuts the number of expressions we need to write in half. I couldn't do that up here with sine because they were not right across from each other. So I had to take each one individually, the 30 and the 150, and add 360 to that. But for tangent, they're right across from each other. So what I can do is say 60 plus 180 in. Actually, I meant to write this in radians a minute ago, so let's do that. That's pi over 3 plus pi in. All right, 180 is the same as pi. Pi over 3 is the same as 60. So this is the trigonometric and the circular version of inverse tangent of the square root of 3. And again, if they asked me for this inverse tangent of the square root of 3, they're asking me for the one value that lives between here and here. And that is either 60 or pi over 3. All right. So there's a lot in there. Not, this stuff isn't easy. It takes a lot of practice. But what we're going to do starting now is be able to do this circle backwards. I will give you the trig function, you give me the angle. All right? So do not shy away from the practice. Practice makes perfect. And Hoven out.